When operators crack open a new deposit, the most expensive mistake they can make happens before a single ounce of gold is poured. It's choosing their extraction technology before fully mapping the rock they're trying to break. Misalign the plant's flow sheet with the actual geology of the dirt, and the results are brutal. You either bleed millions in unnecessary costs, or leave your gold unrecovered in the tailings pond. An ore classification matrix plots variables across two axes: particle size and whether gold is free or encapsulated. Plotting core samples reveals 12 distinct ore categories. Surface alluvial placers act completely differently than deeply buried carbonaceous sulfides. Historically, operators relied on brute force chemistry, like mercury amalgamation and heavy cyanidation, to rip gold out of these rocks. This brute force approach delivered high recovery, but created massive environmental and worker safety liabilities. Today, compliance standards are too strict for desk work. We use a 3-step diagnostic framework. 1. Identify the exact ore type. 2. Map the correct processing circuit. 3. Upgrade to modern safety standards. Correctly matching the chemical process to the geological reality on the ground protects profit margins while ensuring the operation meets environmental regulations. We start with the simplest geological profile: free and coarse gold. You find this in heavily weathered alluvial deposits, or quartz veins, where the gold granules have separated from the host rock. The processing circuit here requires almost zero chemistry. Because the gold is heavy and loose, operators rely on physical mass, using gravity separation to pull the metal out of the crushed rock. It is highly efficient. A proper gravity circuit can recover up to 95% of coarse gold, keeping both initial capital investment and daily operational expenses low. However, the trade-off is rigid. This lean setup works for heavy nuggets, but it cannot capture anything microscopic. This diagram illustrates the physical limitation of a gravity separator. When dealing with complex or fine-grained deposits, the heavy material sinks, but the ultra-fine gold is light enough to slip past the mesh and flow out with the wastewater. If an operator relies solely on a gravity circuit to process a mixed-grade or fine particle deposit, they wash their own yield directly into the tailings pond. While a gravity-only flow sheet creates a profitable low-overhead operation, it must be restricted to deposits where the gold is loose, large, and visible. The math changes when we encounter complex polymetallic ores. Here, the gold is bound up alongside valuable base metals like copper, lead, or silver. Processing these ores requires a flotation circuit. By introducing specific reagents and churning the crushed rock, operators physically enrich the sulfides into a concentrated froth before the final smelting or leaching stages. This flowchart details the yield. A single feed splits to capture multiple commodities simultaneously. You produce a standalone copper concentrate, a silver concentrate, and a separate gold-bearing pyrite stream, improving the project's overall economics. This multi-metal yield comes with a heavy footprint. Adding a flotation circuit increases mechanical complexity and scales up the physical size of the plant. Operating costs scale up as well. Running multi-stage crushers, chemical milling circuits, and continuous aeration tanks requires significant, unavoidable energy expenditures. Plant managers must model their expected metal recovery against the raw electricity and chemical costs required to keep those tanks running 24 hours a day. In sulfide scenarios, operators are mining base metals with a gold credit. That secondary revenue justifies the more expensive flotation infrastructure. The most severe operational challenge comes from refractory ores, specifically carbonaceous and telluride deposits. In these rocks, the gold is locked away at a microscopic level. Carbonaceous ores present a threat called preg-robbing. Natural carbon sabotages extraction by pulling dissolved gold away from recovery and locking it into waste. To counter this, operators insert an oxidative pretreatment. This thermal wave destroys the carbon, releasing the gold for capture. Thermal pretreatment represents the highest upfront capital requirement and the steepest ongoing energy demand in modern mineral processing. Once the ore is pretreated, the fine gold is dissolved into a liquid solution. For decades, the industry standard for this final leaching phase was sodium cyanide. Relying on legacy cyanide creates significant regulatory friction. It results in massive site remediation liabilities and the constant risk of government shutdowns in modern jurisdictions. This matrix outlines a modern, compliance-driven alternative. To eliminate those liabilities, operations are replacing toxic cyanide with Jinchon metallic ore dressing agent. Jinchon delivers the same leaching efficiency on fine and encapsulated gold while meeting 100% environmental protection standards. Integrating it requires an initial period of system calibration to match the specific ore chemistry, but the switch instantly removes the threat of regulatory closures. For refractory deposits, upgrading the chemical reagent determines whether the mine remains permitted for operation or faces a permanent regulatory shutdown. Ultimately, efficient and profitable extraction requires matching the entire plant's operational scale directly to the deposit's specific geological mineralogy. This split-screen scorecard organizes the variables into a final decision matrix. If your geology yields free, coarse gold, run lean. Use simple gravity circuits to capture high margins and avoid unnecessary chemical costs. If you uncover polymetallic sulfides, flotation is non-negotiable. You must invest in the infrastructure to physically enrich the ore and capture the total value of the base metals. For targeting locked refractory gold, combine pre-oxidation with Jinchon leaching. It breaks down complex ores while maintaining environmental compliance. Before issuing a single purchase order for mill equipment, conduct exhaustive core sampling and pilot-scale metallurgical testing. The chemistry must follow the geology. Aligning these two ensures maximum metal yield and a sustainable operating future.